Hello everyone, Chapter 3, Lesson B on Trigonometric functions and the unit circle. So I'll be referring to this word trigonometric by simply trig pretty much for the rest of Chapter 3 and Chapter 4, just to save myself some breath. And then we're going to talk about the unit circle. And the unit circle is a circle on the xy coordinate plane that has a radius of 1 unit. That's why it's called the unit circle, where these points of intersection on the xy axis are as follows. All right, so this would be the x-axis and the y-axis. Okay, so we're going to get into some interesting stuff with the unit circle. Our objectives are to look at the 6 trig functions. You've probably seen 3 of them, sine, cosine, and tangent. We're going to talk about the other 3. We're going to evaluate those functions with and without a calculator, talk domain and period of the sine and cosine function, and I am scratching even odd until later on in the chapter, so don't worry about that. We'll get to that later. So without further delay, let's get started. Okay, so the first thing we need to do is we need to remember our special right triangle ratios. Right triangle trigonometry or right triangle trig you've done in geometry, possibly a little bit of that in higher algebra, I would hope. But we need to recall our properties of these special right triangles. There's 3 of them. Well, there are 2, the 30, 60, 90 and the 45, 45, 90, but I'm going to orient them in the following way. So I'm going to start with our angles of 60, 45, and 30, and I'm going to just write out our side ratios, where the short leg of the 60 degree will be half of the hypotenuse. Notice that all the hypotenuses, I think that's how you'd say it in plural, are 1. That's why we're going to equate these to the unit circle, right? Because the hypotenuse will end up being the radius. And of course, the long leg is root 3 over 2. Now that's closely related to the 30 over in green here, except the 2 sides are swapped. Okay, and with our 45, 45, 90, you can see that these 2 sides, this is an isosceles right triangle, so both these sides are the same length. You will see either root 2 over 2, or you possibly will see 1 over root 2. Those are equivalent. 1 over root 2 is equivalent to root 2 over 2. Now, these can all be verified using the Pythagorean theorem. Okay, so if I took 1/2 squared plus root 3 over 2 squared, I should get 1 squared, right, our hypotenuse. So let's see if it comes out, right? So that'd be 1/4 plus 3/4 is equal to 1. That checks. Okay, that'll happen for each of the others. So these are right triangles. Their sides are accurate because the Pythagorean theorem basically tells us so. Now we need to get into some right triangle trig. I'm going to focus on these first 3 trig functions right here, sine, cosine, and tangent. And I'm going to work with the red triangle first here. So I want the sine of 60 degrees. So here's my angle that I'm referring to. The sine, recall, of any angle theta can be calculated by taking the opposite side over the hypotenuse. Opposite over hypotenuse. So if this is our angle, our opposite side would be root 3 over 2, and our hypotenuse would be 1. Now, the nice part about this is the hypotenuse will always be 1. Therefore, the sine in the unit circle, the sine of theta will always be what will end up being our y value. We're considering this will end up being xy, and in this case y will equal root 3 over 2. So the sine of 60 is root 3 over 2. Let's look at the cosine of 45. Here's my angle. Cosine, I'll put it up here with sine, of any angle theta will be adjacent over hypotenuse. Again, the hypotenuse in the blue triangle is 1. The adjacent side is the leg next to the angle. That'll be our adjacent. So if I took adjacent over hypotenuse, I'd get root 2 over 2 or 1 over root 2, your preference. Okay, tangent. I'm going to kind of throw it up here. Here, you know what, I'll rewrite. Sine of theta is opposite over hypotenuse. Cosine theta, adjacent over hypotenuse. And tangent theta is opposite over adjacent. You may remember Socatoa, right? Sine, opposite, hypotenuse, etc. Okay, so the tangent of 30. Here's my angle, 30 degrees. Tangent is opposite. Well, my opposite side would be 1/2. My adjacent side would be root 3 over 2. If I took 1/2 divided by root 3 over 2, the 2's reduce, and I get 1 over root 3, or root 3 over 3. Okay, let's talk a little bit, now that we've kind of got that down, about cosecant, secant, and cotangent. Okay, so the reason I have both sine and cosecant in red is because the cosecant of 60 is equivalent to 1 over the sine of 60. It's the reciprocal function, right? So it is 1 over whatever the sine of 60 is. If I take 1 over root 3 over 2, that's equal to 2 over root 3. Okay, so you can kind of see what's going to happen here. Secant is going to do the same thing with cosine. So that will be 1 over cosine of 45 degrees. Okay, 1 over root 2 over 2 will equal 2 over root 2. It's okay to leave your answer in that form. Typically in math, we like to rationalize the denominator, which means get rid of the radical. I'll show you how to do that here. I would multiply top and bottom by the radical in the denominator. And what that does, you guys, is it turns root 3 times root 3 into 3. So I should get 2 root 3 over 3. This is a more mathematically elegant way to write that answer, but there's nothing wrong with writing 2 over root 3. That's not incorrect. Okay, so I could write 2 over root 2 as 2 root 2 over 2, or you can see the 2's would reduce. You can see how much simpler that would be, but this would be fine as well. Okay, cotangent is the reciprocal of tangent. So cotangent of 30 would be 1 over tangent of 30. And 1 over tangent of 30 would be 1 over root 3. And you'll see why I chose this one. If I take 1 over root 3, that's the same as root 3. So pretty nice answer coming out of that in the very end. Okay, so we've talked about our original 3 trig functions, sine, cosine, tangent, and we've talked about the reciprocal functions, cosecant, secant, and cotangent. Let's get into some unit circle stuff where this will take place. So here enters the unit circle, and we said that the radius of each of those triangles, the red, the blue, and the green, were all 1. So this point right here was really a triangle that was forming an xy coordinate, an ordered pair. We said that the cosine of 60 was 1/2. That's our x value. The sine of 60 was root 3 over 2. So what we can now determine, right? We're going to plot these points. I'm going to go with 1 over root 2 and 1 over root 2. And here for my 30-degree angle, I'm going to go with root 3 over 2 and 1/2. Is we can equate our sine values and our cosine values to x's and y's. So x is always going to be cosine of theta, and the reason why is because our hypotenuse is always 1, and the y value is always going to be sine theta. So I could say that x equals cosine theta, and I could say y is equal to sine theta. Therefore, tangent, remember tangent was opposite over adjacent, and our opposite value is always our y value, and our adjacent value is always our x value. So now we can find sine, cosine, and tangent relatively easily just by the ordered pairs. And that will happen throughout the triangle, right? Here we are in quadrant 2. The only difference between this point and the point in quadrant 1 is that our x value is negative. Okay, in quadrant 3, that point, both values will be negative. In quadrant 4, our first value, our x value, will be positive, our y value will be negative. And you can see how each of those values will repeat themselves in each of the quadrants. Okay, both are all red, blue, and green. Okay, so there's a symmetry there. Now, there are some special points. I mean, outside of those red, blue, and green, the only other points that we like to work with are called quadrantals. These yellow points are called quadrantals. Okay, anytime you land on a vertical or a horizontal axis, that's called a quadrantal. So let's real quick, I'm just going to do a couple examples. I didn't plan this out, but I'd like to do it. What would be the sine of pi over 2? Well, first of all, you need to locate it on the unit circle. Pi over 2 is the same as 90 degrees. So the sine of 90 degrees would put us right here. Okay, and recall that the sine is the y value. Well, what's the y value at that location? It would be 1. What would be the sine at pi? Well, the sine at pi would put us over here at 180 degrees. The sine at pi is 0. That's our y value there. What would be the cosine at pi? I could also say this is synonymous. What's the cosine at 180? Well, I would find the x value would be negative 1. You're starting to navigate the unit circle based on locations, right? So based on these triangles and their side lengths, and the fact that their hypotenuse is 1, we can then determine what the sine, cosine, tangent, and etc. would be. Okay, so let's get into a couple of examples here down at the bottom. So the sine of 120. Well, the sine of 120, first of all, you need to know your angle measures. This will be 60. This red will be 120. Okay, over here in quadrant 2. So the sine of 120 will be the y value there, which will be square root of 3 over 2. Okay, what about the cosecant of 120? Well, the cosecant at 120 will be the reciprocal of the sine of 120, which will be 2 over root 3. I could rewrite that if I want to as 2 root 3 over 3. Okay, let's look at another example here, the cosine of negative 45. Well, the cosine of negative 45 will be this angle here, right? This will be negative 45 degrees. Or you could call it negative pi over 4, right? Converting to radians. What would that coordinate be? Well, it would be a positive x and a negative y. Right, we're in the 4th quadrant. I almost wrote a 4 there because I was about to say 4th. Okay, what would the cosine be there? What would be the x value there? 1 over root 2. What would the secant there be? Well, it would be 1 over the cosine, which would be root 2. Okay, let's look at the tangent of 0. here's 0 degrees. This is also coterminal with 2 pi. So the answer to tangent of 0 would also be the answer to tangent of 2 pi. So what is the tangent of 2 pi? Well, we can take y over x, so 0 over 1, which would equal 0. Well, the cotangent would then be 1 over 0. What would that be? That would actually be undefined. So the cotangent function is undefined at 0 degrees. It's also undefined at 2 pi, at 2 pi, and at 4 pi, and at 6 pi, etc. So you can see how coterminal angles will yield you similar ratios. So while we're thinking about that, let's talk about it. What is the independent variable here? Well, the independent variable here is an angle. So our inputs are angles. What are our dependent variables? I don't know how to spell dependent. Dependent. I think that's right. Okay, our ratios. So we're plugging in angles, we're getting out ratios. Okay, let's look forward at what we're doing next, and that will come into play, I believe, on the last slide. So let's get going. So if you haven't already filled out your unit circle, I would take a snapshot of this unit circle here. Very important. It's got degrees, it's got radians, it's got all the ratios. The author of this decided to use, for its 45s, decided to use root 2 over 2. Totally fine. I prefer 1 over root 2. That's just personal preference. Okay. But if there's an angle that doesn't fit on here, isn't either coterminal with it, number 4 here, I don't see 55 degrees, you will have to use your calculator. And then what you're going to want to do is make sure you're in the correct mode as well. So before we get to that, let's do a few of these problems. So secant pi over 4. I'm going to find pi over 4. Okay, cool. How is the secant related to either the cosine or the sine? Well, I would say that the secant is the reciprocal of the cosine. And as you get good at this, you don't have to write down this initial step. But the cosine of pi over 4 is the x value, root 2 over 2. Okay, the reciprocal of that is 2 over root 2. So right there, you're done. That's the secant of pi over 4. If you choose to go further, you can, which would be, I believe it ended up being root 2. That's equivalent. Okay, let's go tangent pi over 6. Locate pi over 6. Here we go. Tangent of pi over 6 is the cosine of pi over 6. Excuse me, sine over cosine. Sine over cosine. So that's 1/2 over the square root of 3 over 2. As we did before, I think we just did this one. The 2's will reduce, and you'll get 1 over root 3. Or you could write that as root 3 over 3. My 3's are poor here, but either one of these is acceptable. All right, excellent. Okay, on to the next one. Let's find 240 degrees right here. Cotangent. So the tangent was y over x. Okay, the tangent was y over x. So the cotangent will be x over y. So let's take x over y here. It looks like negative 1/2 over negative root 3 over 2. Interesting enough, the 2's reduced. We're going to get the same answer that we did for part 2. The negative reduces, and we get 1 over root 3, or root 3 over 3. That's interesting. Okay, cosine of 55. Now here's where I won't be able to locate 55 on my unit circle. I take out my calculator. Please pay attention here, and make sure you're with me. First thing you need to do is you need to press the mode button. Okay, so press mode. And ensure you want to go down to, it'll say radian and degree. Make sure degree is highlighted in this case because 55 is in degrees. Okay, go back to your home screen. by pressing secant mode. That'll quit you back to your home screen. And press cosine and type in a 55. Close the parentheses, press enter. All right, so cosine of 55 to 3 decimal places is 0.574. Now, what does that mean in the context of this? Okay, so if I went out 55 degrees, this is my best attempt at 55 degrees. 55 degrees. It's asking me what is the x value for that. Well, the x value for that comes out to be 0.574. Okay, so 55 puts my x value a little bit further to the right than 1/2. Right? I gotta shift that over a little bit, so it makes sense that that would be 0.574. Okay, if you have an acute angle between 0 and 90, you can expect your cosine and your sine to be positive. So just so you know, positive, positive here. We'll get negative, positive here. We'll get negative, negative in quadrant 3. And we'll get positive, negative in quadrant 4. Okay, so now let's look at the tangent of 270. Remember, the tangent is equal to opposite over adjacent, or y over x. Okay, so as we look at 270, 270 is a quadrantal. It's right here. Okay, we're going to take the y value over the x value, and that's going to be undefined. So the tangent has a discontinuity at 270 degrees, or 3 pi over 2 radians. Okay, let's go to number 6, negative 19 pi over 6. Now, I don't see it on my unit circle here, but whenever I see a pi over 6, I know that I'll have a coterminal angle to that. So I'm going to add 2 pi to this until I get an angle within 0 and 360. So if I add 2 pi is actually 12 pi over 6. Right, so I'm going to add 12 pi over 6. Well, if I add negative 19 pi over 6 plus 12 pi over 6, I get negative 7 pi over 6. Okay, now I'm going to add another 12 pi over 6 to that. That's going to give me 5 pi over 6. So negative 19 pi over 6 is coterminal. Why coterminal angles are important, to 5 pi over 6. So they should have the same x and y value. Okay, so where is that? Let's see. 5 pi over 6 is right here. So the sine of negative 19 pi over 6 is equivalent to the sine of positive 5 pi over 6, which is equal to 1/2. And there you have it, guys. That's how you use the unit circle to evaluate trig functions. Okay, I got one more slide here that I'd like to talk about, and then that'll be it for this lesson. All right, so here we have it on the last slide. I want to talk about the domain of sine and cosine. So we talked about independent and dependent variable. So the sine of an angle gives me a ratio of some sort. So my input is an angle. So my domain has to do with angles. Now there's no restriction. There is absolutely no restriction on the domain. Okay, so get that into the head right now. No discontinuities. We don't have to worry about vertical asymptotes or holes or anything like that where we have a discontinuity within the domain. The domain of sine and cosine. Now keep that straight. Sine and cosine. Tangent, cotangent, all those other functions different. But the domain of sine and cosine is all real numbers. The period of sine and cosine is interesting. The period is when the outputs start to duplicate themselves again. So when you think of a circle, the outputs start to duplicate after one full rotation. So the period of sine and cosine is equal to 2 pi. After every 2 pi units, you'll see the outputs duplicate themselves again. So if you were to look at the unit circle, wow, great circle. Tired, I guess. Okay, I get an output of, let's say we're talking about sine, right? We're talking about our y values. Oh wow, that was really poor, because that's not accurate at all. It should be 1, 0. There we go. Okay, the period. Okay, now this is interesting, but when's the next time I get a 0? Well, I'm getting positive y values, then I hit a 1, then I come back down, and I hit a 0, right? So you might think, well, it duplicates itself after pi units. That's not true, because now the values for y are negative to -1 and back up to 0. So in essence, and this is a little bit further ahead than I thought I'd get today, but a sine function starts at 0. At pi over 2, its output reaches 1. At pi units, its output is back at 0. At 3 pi over 2, it's an independent variable. Its output is -1. And then at 2 pi, it's back to 0 again. So the graph of sine, one period of the sine function, ooh, that wasn't great, it should look like that. You can see how then it will start to duplicate itself the next time around. So a period of pi equals 2 pi. Cosine will be slightly different, but its period will be exactly the same. All right, guys, that's all I've got for lesson B. Hope it went well. See you in the next video. Shoot me some questions if you got them.